All right, everybody, welcome to Math with Grace. Today we're going to be working through Pre-Calculus, Unit 5, Section 1. Unit 5, Section 1 begins on page 5, and it's titled Identities and Addition Formulas. It says here that if an equation containing a trig functions is true for all values in the domains of the function, the equation is called a trigonometric identity. Sliding down here, we see that the reciprocal identities are the definitions of reciprocal functions. So these are considered identities. We've done them before. So this is just a little bit of a review. So it says in the following example, the reciprocal identities are used to simplify expressions. So if we're simplifying sine theta times secant theta times cosine theta, we want to use the reciprocal here to change the secant, okay, into 1 over cosine, right? Secant is 1 over cosine. Then we can cancel out our cosines, become a 1, and then we just are left with sine. So it's as simplified as it gets, right? We're down to one trigonometric one trigonometric function. Let's turn the page. At the top of page 6, we have another example. It says simplify tangent theta, cosine theta, cotangent theta. And again, we choose the cotangent, right, to substitute in its identity, which is 1 over tangent. That allows our tangents to cancel out, and we're left with just the cosine, okay? It says the tangent and cotangent functions can be expressed in terms of sine and cosine. So they're good ones to go to. All the reciprocal functions kind of are nice to change because it gets it down to a simpler form, right? And so since they can be expressed in the term of sine and cosine, okay, using the fact that tangent equals opposite over adjacent, tangent of theta, right, is opposite over adjacent, or if we plot this point x, y, it's y over x, then we can substitute x and y, and you can whittle it down even more. So tangent is the sine over the cosine, because y is our sine and x is our cosine. Remember our unit circle, okay? The first number in the coordinated pair, right, was the cosine, and the second was the sine. So tangent is sine over cosine. Since the cotangent function is the reciprocal of the tangent function, it can also be written in terms of sine and cosine, or the cotangent equals cosine over sine. So the quotient identities, remember we're going to be learning some new identities. Some of them are kind of, the derivative is kind of complex, and so I won't be going through every step. We'll just be looking at what the identities are, okay? But for the quotient one, it was fairly straightforward. So here are the quotient identities, okay? At the back of the book, there is a great section. Let me see what page it's on here. Yeah, right back here, page 44. It starts here on page 43 and 44 and beyond, for that matter. And it has all of this stuff laid out real nice for you to reference while you're doing your work. Okay, so let's not underutilize those review pages because they're great. They've put all the important information in one place. Okay, but here are our quotient identities. Not asking anybody to memorize anything. But definitely know where to find the information, okay? So here's an example. Simplifying sine theta times cotangent of theta. Well, if my cotangent of theta is equal to cosine over sine, I can substitute that in. My sines cancel, and it equals cosine of theta. The next example is to simplify cosine times sine times cosecant times secant plus sine times tangent times cotangent. So there's obviously a lot going on here, but if we take these reciprocal ones and we substitute in their identities, right, we can cancel some things. We can cancel a cosine and a sine and a tangent, and we're left with 1 plus sine of theta is what it whittles down to. Okay, again, we're back to one trigonometric function, and that's great when we're trying to simplify. All right, the next set of identities are called the Pythagorean identities, okay, and they are set up because of the Pythagorean theorem. All right, so again, the information is here. I think we all understand the Pythagorean theorem. If we're looking at this angle here, it would be that x squared plus y squared is equal to r squared, which is what they've set up right here, right? If x is the cosine and y is the sine, then they have cosine squared plus sine squared equals 1, because remember, on the unit circle, the radius is always 1. That's what makes it a special thing. So that is a Pythagorean identity. And there are a couple more if we look at the top of page 7 here in the first column, that they make because of other identities into that first one, and thus the Pythagorean identities all in one place are here. So cosine squared plus sine squared equals 1. 1 plus tangent squared equals secant squared, and cotangent squared plus 1 equals the cosecant squared. Okay, so these three are our Pythagorean identities. Looking at this next example, or set of examples, I should say, they want to show us in these couple examples here how our identities can be algebraically manipulated, just like we would manipulate a 2x plus 3y equals 4 equation to solve for y, right? To solve for a specific thing. So in this first one, it says, by subtracting cosine squared from both sides of this identity, you could write sine squared equals 1 minus cosine squared to try to get it to look more like something that's in the problem that you're working on, right? Squaring both sides of the identity of this identity results in this identity, okay? Which then maybe we could substitute this in or whatnot. If cotangent is 1 over tangent, then tangent equals 1 over cotangent. So they're just manipulating algebraically some of these equations to have them in a different order, basically. Identities are used to write trigonometric expressions in a simpler form. This might involve reducing the number of trig functions or eliminating a fraction. So for this example, we have a fraction, and it continues on the top of the next column, so we'll slide up there in a second. But we have sine theta times secant theta over cosine squared of theta. And they want us to express this in terms of tangent. Now, there isn't even a tangent here to start with, but we know that tangent is equal to sine over cosine. Okay, and then the other identity that we have with a tangent in it right now, other than its just basic identity, which is here pretty much, is 1 plus tangent squared equals secant squared. Okay, now what they do, we're going to slide up to the top of page 7. Okay, what they do is they substitute in, but first they break apart their fraction into two pieces, right? So they have the sine of theta over cosine theta, because we have cosine squared, so they broke it into two pieces. And then we have secant theta over cosine theta. This here is the tangent. So now they've replaced it with a tangent because that is our goal, right? That's what we're trying to get to. And then they have the secant over 1. They've pulled the cosine out and made it 1 over cosine. So they've separated this fraction into two parts. Secant theta over cosine theta. Okay? Secant theta is equal to 1 over cosine. So to make the substitution, they change this to a secant. Okay? Because that's what secant theta equals. So now we have tangent times secant squared. To use the 1 plus tangent squared equals secant squared, we make that substitution here. So we know that secant squared equals 1 plus tangent squared, and then they distributed, right? Tangent theta times 1 is tangent theta. Tangent theta times tangent squared theta is tangent to the third power of theta. Now all of them are tangents, and that's what was asked of us back here, right? Express it in terms of theta. Now this next example here is actually the same example, except they're doing it as with an alternate solution. And basically, they're doing it this way to show us that there are different ways to achieve the same result, as it is true with math, advanced math in general, right? And so they still have sine of theta times secant theta over cosine squared, and they want it in terms of tangent still, okay? They rewrite the fraction this time as a product, right? Sine of theta times secant theta times 1 over cosine squared of theta. They still use the secant theta equals 1 over cosine. And I think this is supposed to be 1 over cosine squared equals secant squared. Yeah, this is just a little typo. So this is supposed to be 1 over cosine squared equals secant squared. So 1 over cosine squared, they changed it to a secant squared. And then this secant, they changed to 1 over cosine. So this should just be a 1. There shouldn't be a squared there, because then they combine these two things to make sine over cosine, which we know is our tangent, right? So then they end up at the same spot. Sine over cosine was our tangent. For our secant squared, they substituted in 1 plus tangent squared, and we ended up with the same answer, okay? So different, tactic, right? A different way to go through it, but we ended up with the same answer, and that is what is important, okay? Sometimes these types of problems are going to be like that. All right, let's turn the page. Top of page 8, we have another example of sine squared over cosine plus cosine squared over cosine equals sine squared plus cosine squared over cosine. And they want us to simplify. I mean, this, I guess if this was our original problem, then of course it's going to equal this, because all they did was add the two fractions. They both have a common denominator right now, and so they added it up. Sine squared plus cosine squared is equal to 1. So they ended up with 1 over cosine, which is actually the same as secant. Okay, we're getting rid of the fraction part. Okay. It says here, identities can be used to determine all of the trig function values of an angle when one value is known. Okay, here's an example of that. Find the 5 remaining trig function values of the second quadrant angle theta if the secant theta is equal to negative 3 over 2. Okay, now when they say the 5 remaining, right, there's sine, cosine, tangent, then there's cosecant, secant, cotangent. Those are the 6 in general. They're giving you 1. They want you to solve for the other 5. It says the cosine of the reciprocal of the secant, so cosine, if secant is negative 2 over 3, then cosine is negative. If secant is negative 3 over 2, then the cosine is negative 2 over 3, okay? And they have here that the cosine squared plus sine squared equals 1, so that tells me that negative 2 over 3 squared plus sine squared must equal 1. They square it and then subtract it from the other side. Right? It's positive here, so they have to subtract it from both sides. So they end up with positive 9 over 9 minus 4 over 9, which gives them a positive 5 over 9. Then they take the square root of both sides and get plus or minus the square root of 5 over 3. Now, sine, because it's the second quadrant, is only going to be positive, so we don't need to worry about the negative part. So now this is the second. They've solved for, they gave us 1, they solved for the second one here. This is the third one, and we have 3 more to go. If we already know the cosine and the sine, we can get the cosecant, right, by flipping this over, taking the reciprocal. Now remember, when you have a radical in the denominator, it reminds us up here, right? We can't do that. We have to cancel out the radical, and we end up with 3 times the square root of 5 over 5. Then we have to find the tangent. The tangent is the sine over the cosine. Okay, so they took the sine, square root of 5 over 3, okay, and they put it divided by negative 2/3 and end up with negative square root of 5 over 2, okay. Last one is the cotangent, which is just a reciprocal of this, but again, because the square root of 5 would be in the denominator, we have to work to cancel that out, and we end up with negative 2 times the square root of 5 over 5. And that is 1, 2, 3, 4, 5, 6 tangent or trigonometric functions that go with this. Now, that is one way to solve this. And just like we talked about a minute ago, there being multiple ways to solve, I want you to be able to think about it in a different way. I'm a little bit more of a visual person. And so to me, a second quadrant angle, okay, would be over here, right? And it says the secant is negative 3 over 2. Well, if we draw our reference angle in here, right, and we have negative 3 over 2, I know that this is going to be the secant is the opposite or the reciprocal, right, of the cosine. And if cosine is adjacent over hypotenuse, then this is hypotenuse over adjacent, right? So this is positive 3 and this is a negative 2. And with that, I can solve this pretty much the same as they did, right? With the Pythagorean theorem, except without the fractional part. Because I would say that x squared plus negative 2 squared equals 3 squared, or x squared plus 4 equals 9. X squared must equal 5, so x is equal to the square root of 5. X being this value here, okay? Which I guess technically is our y, but we're just solving a problem here. Now I can find the cosine. Well, the cosine we already knew was negative 2 over 3, right? Negative 2 over 3. The sine is the square root of 5 over 3, okay? And then we just flip the other ones over and we'd have to mathematically figure them out. But for the tangent is the opposite over the adjacent. So square root of 5 over negative 2, or negative square root of 5 over 2. Okay, so if this way, setting it up like this works for you, then set it up like this. Like this, when I read this example, the first thing I thought of was drawing my reference angle. Okay, because we've been doing that in other problems too. So it should be something we are comfortable with. Now, of course, just working through the problem this way with the identities is perfectly fine as well. But if this helps you see, because we still did the identity right here, okay, that's still the same thing. But if this helps you see what's happening, then obviously draw the reference angle and work through it that way, okay? Both ways end up at the exact same answer, so both ways are perfectly valid. All right, let's take a look at some of these problems together. Taking a look at problem number 3, it says simplifying sine of theta over cosecant of theta. Well, we need to remember what a cosecant is, right? So if we rewrite this as sine of theta over 1 over the sine of theta, because that's our cosecant's identity, right? But we can't divide by a fraction, so we end up with the sine of theta times the sine of theta over 1, right? We take it by the reciprocal, flip-flop, multiply. So we take the reciprocal and then we multiply. We end up with sine squared of theta, which is letter D. All right, this book doesn't give us a whole lot of room to work, so we're kind of just going to be scribbling into the middle here. For number 4, they want us to simplify 1 over the cosecant of theta times 1 over the sine of theta. Well, again, if we focus on this cosecant, the cosecant, or 1 over the cosecant, is the same as 1 over the sine of theta, right? Times the sine, or 1 over the sine of theta. this, again, needs to be flip-flop multiply, but since it's being multiplied by a 1, we can just rewrite it as the sine of theta times 1 over the sine of theta, okay, which these cancel, and we're left with just a 1, which is letter A. Okay. Taking a look at one more here, we want to look at simplifying 1 over the cosine theta plus tangent squared over the cosine theta, combining them because they have the same denominator. We get 1 plus the tangent squared of theta all over the cosine of theta. Now, 1 plus the tangent squared of theta is what from our identities? Yeah, it's the secant squared of theta, okay, over cosine of theta. All right, now, since I have a secant squared here, I am going to change this cosine over to a secant as well. So that gives me, and I'm doing these real basic so you can see the step, secant squared over 1 over secant theta, okay? Now, I can't divide by a fraction, right? So it's going to end up being the secant squared of theta times the secant of theta over 1, right? We took the reciprocal of this and we multiplied, flip-flop multiply, and we end up with the secant cubed of theta, which is letter D. All right, so it's not always the smallest one that we're going for, like cosine is the most basic, right? But it's not always the one that's the best choice to get. Since this was already a squared, it was best to just go that direction. All right, let's take a look at number 8. They want us to simplify the square root of tangent squared plus 1 over cotangent squared plus 1. Well, both of these are Pythagorean identities. The tangent squared plus theta, or not plus theta, tangent squared of theta plus 1 is the same as the secant squared of theta. And one we haven't really used yet is this cotangent squared of theta plus 1, which is the same as the cosecant squared of theta. Now we have a square over a square, so when we take the square root, we're left with secant of theta over the cosecant of theta. Okay, but as you can see, they want it to be, that's not a choice here, so we can simplify this even more. The secant of theta is the same as the 1 over the cosine of theta, and the cosecant of theta is 1 over the sine of theta. I can't divide by a fraction, so we're going to flip-flop multiply or take the reciprocal. So I have 1 over the cosine of theta times the sine of theta over 1, which is equal to sine of theta over the cosine of theta. And because sine of theta is equal to cosine of theta, or sorry, sine of theta over the cosine of theta is equal to the tangent of theta, then our answer becomes D. Now you might be wondering, well, how am I supposed to know that I continue to simplify here? Well, some of it is a guess and check system, right? I know these two things would give me a sine over cosine eventually. But even if it gave me a cosine over sine, I know that that is a simpler form, right? We're going from two trigonometric functions here down to one. And so I knew by simpling these two down to their simplest pieces would give me one trigonometric function. And that's really what the point is of simplifying, right? Getting down to its simplest form. So this was great, but we could take it one step farther. Sometimes, just like factoring in algebra, right? Sometimes something could factor out, but it doesn't always cancel. But sometimes we have to take that extra step to see, let's factor it another part, or let's simple it down a bit, and then see what happens. Okay? All right, go ahead and finish these and meet me back here for the next part of this section. The next part of this section begins on page 11, and it's entitled Proving Identities. So here's where we're at so far. A nice little consensus of what we've learned. We have the quotient identities, the reciprocal identities, and the Pythagorean identities. It says the goal of proving an identity is to get each side of the equality to be the same. So we have something equal to something else. We want them to be the same. This is done by simplifying the trig expressions that make up the equality. It's important to distinguish between the process of proving a trig identity and solving an equation. When we're solving an equation, which usually equals 0 or equals something, right? We use the properties of equality, right? We add or subtract from other sides. We multiply or divide on both sides. But when we're proving an identity, we don't do that. So this is what this is saying. We don't do that. We are substituting and simplifying one side or both until they are the same. It says here, the following is a list of some common strategies for proving that a statement is a trig identity. The first one, substitute. Use identities that you know to substitute a quantity for its equal. It's often helpful to put everything in terms of sine or cosine. Perform operations, adding, subtracting, multiplying, and dividing. And that is, again, on one side of the equal sign. Reduce fractions, factor, or multiply by a conjugate. Okay. Key point, properties of equality may be used to rewrite a known identity prior to making a substitution. Okay. Let's turn the page. The first example here on page 12 asks us to show that sine times cosine times tangent is equal to tangent times cotangent times cosine squared is an identity. Prove that this is an identity. We don't want to move everything to one side or the other because we want to keep everything that's on one side there and everything on the other side there and prove that they are the same thing. So they have the problem here. They're substituting the tangent for sine, cosine, sine over cosine, and substituting the cotangent with cosine over sine. And when they do that, this is what it looks like. And so we're going to cancel here and cancel out this whole thing, right? So it simplifies to sine squared equals 1 minus cosine squared, okay? And if we know the Pythagorean theorem, right, the Pythagorean identity tells us that sine squared plus cosine squared equals 1. So that sine squared must equal 1 minus cosine squared, right? If we rearrange that, so 1 minus cosine squared equals sine squared. So this is an identity because both of the sides are equal. All right? It says, note that both sides of the equation were simplified in this example. So we simplified both sides of the equation. Here, though, we don't need to simplify both sides because one side is already, I mean, it could be made differently, but it is just one thing. So show that cotangent plus sine over 1 plus cosine is equal to the cosecant. So they started by making the substitution for cotangent, okay? And then they found a common denominator between these two things so that they could add the fractions together. When they added their fractions together, they had cosine plus cosine squared plus sine squared all over the common denominator. Okay. Then they substituted 1 for cosine squared plus sine squared, right? Right here, cosine squared plus sine squared, they changed that to a 1. Now we have cosine plus 1 over the common denominator. They reduced the fraction by factoring the common factor of 1 plus cosine, right? Here's 1 plus cosine, here's a 1 plus cosine, so those cancel, and we're left with 1 over sine. Well, 1 over sine is the same as the cosecant of theta, and so cosecant of theta equals cosecant of theta. On this example, only the left side of the equation was simplified. And it says here that there is no specific method or series of steps for proving trig identities. There is no one surefire way, do this, do that, do this, to show these identities, right? It's kind of a guess and check system. Just like geometric proofs, you need to think of a plan and be sure you can justify it. Okay, you got to think of a plan, and maybe you work your way through and it doesn't work. You've got to go back and try a different method. Let's take a look at this example. For here we have the cosecant squared times the tangent squared equals 1 plus the tangent squared. So we've got to think, are any of these resemble something else? One of our identities. Remember, just this page ahead had a nice little breakdown, and also the pages at the end. But here's a nice little consensus of what we've learned already. And one of these, 1 plus tangent squared, is on here, right? 1 plus tangent squared equals secant squared. So that is definitely a possibility. But let's take a look at how they've got two different solutions here. So let's take a look at what they've got. So they took the cotangent squared plus 1, and they substituted that for this cosecant squared. Okay? And so they're here. Then they distributed to get tangent squared times cotangent plus tangent squared equals, and they're leaving the left side alone, or the right side alone for now, or actually for the whole thing. And then they substituted for this tangent squared. 1 over tangent squared is cotangent squared. So they substituted 1 over tangent squared for that cotangent, which allows us to cancel here, and this just becomes a 1 plus tangent squared. Now, I personally would have taken it the one extra step and simplified this so it wasn't a 1 plus and a 1 plus, right? It would just be a consecutive thing. But they didn't take it that far, and so if that's good enough for them, that's good enough for us, right? And then they do it a different way, okay? So they substituted, same problem, except this time they are substituting 1 over sine squared for the cosecant part, which gives them, and they're also substituting sine squared over cosine squared for the tangent squared. So it ends up looking like this. They canceled here, and they ended up with 1 over cosine squared equals the right side, because they haven't changed anything on the right side. The rest is up here at the top of page 13. Then they substituted the secant squared for this 1 over cosine squared. So they have secant squared equals 1 plus tangent squared. Okay. The identity 1 plus tangent squared equals secant squared. So that's where I would have changed this side to secant squared and just had secant squared equal to secant squared. But they continue to write it like this. Again, I wouldn't mark it wrong if you wrote secant squared of theta equals the secant squared of theta rather than this 1 plus tangent squared equals 1 plus tangent squared. They're both the exact same thing, okay? But that's the example the book is giving us for now, okay? Let's look at this next example here, page 13. We have cosine theta over 1 plus sine theta equals secant theta minus tangent theta. Prove that it is an identity, okay? Though that instructions there show that this is an identity, tells us the process that we need to use, right? We're not trying to solve for something. We're showing this to be an identity. So it says in this problem, multiply the conjugate of the denominator and then use the Pythagorean identities to make a substitution in the denominator. So remember, a conjugate is exactly the same denominator except the sign is different. So we have 1 plus sine here in our denominator, so the conjugate is going to be 1 minus sine. And we do the same thing over itself because now this is actually technically a 1, right? So we're multiplying by a 1, so we're not changing the basic of the problem. So then they multiplied this out, right? This down here becomes, you take the 1 and you square it, you put a minus in between, and you take this, the final term, which is a sine theta, and you square that. So it's square, square, right? With a negative in between. So 1 minus sine squared is now the denominator. The numerator is just the cosine times 1 minus sine theta. And they don't seem to be multiplying that through at all, because 1 minus sine squared is equal to cosine, right? That's the Pythagorean identity. Sine squared plus cosine squared equals 1. So cosine squared equals 1 minus sine squared, right? They just manipulated the identity so they could substitute in this cosine squared. They haven't done anything on the right, and it doesn't look like they're going to, okay? Now we can reduce. This cosine takes off one of the cosines here, so now we have 1 minus sine of theta over cosine. Then they break the fractions right back apart, right? So here we multiplied by the conjugate and kind of made a larger fraction. Now here they're breaking it apart. So they have 1 over cosine minus sine over cosine. Well, sine over cosine is tangent. 1 over the cosine is the secant. So they've ended up right where they started. And the reason they didn't change any of this is because they don't want the fractions, okay? That's why they didn't change this side, because changing this side would have just made more fractions. And so we're trying to get rid of the fractions is what the simplifying is. So they compared it to this one, which is the exact same problem, except they put everything into a fractional form. But a fractional form isn't really considered simplified. But you could. I mean, they did here. Okay, so multiple steps, multiple different ways you can do these problems, always the same answer, right? Okay, top of page 13, second column. Sometimes equations are impossible to solve when they contain more than one trig function. Identities can be used to express these equations in terms of a single trig function. Really, that is simplifying things, right? Here's our example. Solve, different than show, right? We're not showing an identity. We're actually solving a problem here. Solve secant squared theta plus tangent theta minus 1 equals 0 for this parameters, right? Theta has to be on the unit circle, 1 revolution of the unit circle. So they use the Pythagorean theorem for secant squared equals tangent squared plus 1, and they substitute this in, okay? Now we have the tangent squared plus tangent equals 0 because our 1's cancel each other out and our 0 is still there. Now they can use factoring to pull out a tangent because both terms have a tangent in common. That leaves tangent plus 1 equals 0. So now they can set each one equal to 0, right? The 0 product. Tangent of theta must equal 0, or tangent plus 1, or tangent equals 1, okay? And then what angle measurement of theta is at each of these points? Pulling out your unit circle, we can find that tangent of 0 is 0, tangent of -1 is all these other pieces, okay? So unit circle still going to be useful in this section of the book. This example here at the bottom of page 13, the last one on this page. Solve 2 times the sine squared of theta plus 3 times the cosine of theta minus 3 equals 0 for the parameters of the unit circle, but now we're talking about degrees instead of radians, right? This tells us how to write our answer. Here it was in radians, here we're talking about degrees. So they want us to use the Pythagorean identity to make a substitution for sine squared, right? Bring it down to something else, or at least a cosine-ish looking things, right? It's because sine squared is equal to 1 minus cosine squared. Then they distributed the 2. So we have 2 minus 2 cosine squared plus 3 cosine minus 3 equals 0. They've combined their like terms and ended up with a -1. Then they divided out or removed their negative sign, basically. So they changed all the terms. So this became positive, this one became negative, this one became positive. And then they factored. You know, what is the factorable in this problem? Now, you could have done the quadratic formula with a 2 as your A, your B is -3, your C is 1, if you weren't sure how this factored with a 2 for your cosine, or your 2 for your coefficient, right? But they factored it into 2 cosine minus 1 times the quantity cosine minus 1. And then they set each of those equal to 0 and solved for their answers. Okay? Cosine is either going to be 1/2 or 1, and these are the angle measurements that have that cosine. All right? Okay, let's turn the page. All right, on the next page are the problems we're going to work through. Let's take a look at number 19. It says secant of theta minus secant of theta times the sine squared of theta. And they want us to simplify. All right, so for number 19, we have secant of theta minus secant theta times sine squared of theta. Secant is in both terms, so we're going to go ahead and factor that out. So I'm going to factor out the secant of theta, and that's going to leave me with 1 minus the sine squared of theta. Okay. Remember, secant is the 1 over the cosine, so now I can change this to a cosine. So I'm going to change the secant to 1 over the cosine of theta times 1 minus the sine squared of theta is cosine squared of theta. I can cancel a cosine, right? So that becomes a 1. And then I'm just left with the cosine of theta. Letter B. Okay. They both had the secant in common. The secant is a cosine. So in order for me to cancel out a secant, I would need a cosine. By pulling the secant out by itself and leaving 1 minus sine squared, that allowed me to transfer this over or substitute in a cosine squared, and then I could cancel some cosines, and I have 1 left. Okay? Let's take a look at number 22. For number 22, we have sine of x over cosecant of x plus cosine of x over secant of x. Well, basically, we have the sine of x over 1 over the sine of x plus cosine of x over 1 over the cosine of x, right? That's what the cosecant and the secant stand for. So I end up with sine squared x, because I have to flip this over, take the reciprocal, and it becomes sine of x times sine of x over 1, right? That's the reciprocal. So we get sine squared of x, and then the same thing happens here. So cosine squared of x, and the sine squared plus the cosine squared equals 1. So my answer is B. Okay? I want to come over here and take a look at problem number 27. Now, it's interesting to me that in this homework, they don't actually have you proving any identities, which is like a whole part of that section that we just did, but who am I to say? But let's take a look at number 27 here. It says, simplify the trigonometric expression tangent squared of x over secant squared of x plus cotangent squared of x over cosecant squared of x. So let's take a look at this. So tangent, remember, is equal to sine over cosine. So tangent squared is going to be sine squared over cosine squared. And that's going to be over secant squared. And remember, secant squared is 1 over cosine squared. Okay. Plus, I'm going to move up here. Cotangent is the opposite of this. So it's cosine squared over, what is the next? Sine squared. And that's all over cosecant squared, which is 1 over the sine squared. When we take the reciprocal of this and multiply it by the numerator, we have our sine squared over cosine squared times cosine squared. So my cosines are going to cancel, and I'm left with sine squared. And then the opposite happens here, right? I'm going to have cosine squared over sine squared times sine squared. So my sines are going to cancel, and I'm left with cosine squared. And sine squared plus cosine squared, just like in the last problem, is 1, which kind of got buried there, but the answer is D. All right. Let's take a look at problem number 28. Now, I feel like this is probably not necessarily going to fit very easily here on this work, so I might just kind of, here, we'll section off a piece right here, and we'll call this 28. So since I'm doing 28 over here, I'm going to just rewrite it real quick so I can reference it right here. So I have 4 sine squared plus 4 cosine minus 5 equals 0. Now, I don't write the theta or the x or whatever. It's just to save time, okay? Now, because this is just a regular cosine, I definitely want to change this sine squared over to cosine. So 4 times sine squared can be substituted with negative or 1 minus cosine squared, right? That's Pythagorean identity. Plus 4 cosine minus 5 equals 0. Let's distribute. So we have 4 minus 4 cosine squared plus 4 cosine minus 5 equals 0. We're going to combine our like terms and have negative 4 cosine plus 4 cosine minus 1 equals 0. Now, because we want this to be a positive, we are just going to change all of the signs like this. So now we have plus, minus, plus, and then we're going to factor. Now, 4 cosine is a perfect square, so this is going to be 2 cosine here and a 2 cosine here. To get a positive 1, but have negative middle term or linear terms, then I have a negative 1 and a negative 1. Just to double check, 2 cosine times 2 cosine is 4 cosine squared. 2 cosine times negative 1 is negative 2 cosine. Negative 1 times 2 cosine is negative 2. They make that negative 4. And then negative 1 times negative 1 is positive 1. So that works out perfectly. So 2 cosine minus 1 equals 0. I'm not going to do both because they're exactly the same. And so that tells me that 2 cosine equals positive 1, or cosine equals 1/2. Okay. Cosine equals 1/2 is a special measure of 60 degrees. So letter D, 60 degrees. Okay? All right. Go ahead and finish the rest of these on your own, and then meet me back here for the next part of this section. The next section begins on page 16, and it's called the cosine addition formula. What this is going to allow us to do is to add the cosine of 2 different angles. Now, there's a lot of information here on this page about how this formula is derived using the distance formula and a lot of, not complicated math, but math I know that if I try to read out to you, I will just stumble over it for the next couple of minutes. So I'm not going to read out everything that is happening here, but we are going to jump to right here and see that this formula is known as the cosine addition formula. So the cosine of the quantity alpha plus beta is equal to the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. So to add these 2 angles, you can't just add the angles and find the cosine of that. It doesn't quite work, because if we just look over here real quick, right, the angles they just don't line up. And so adding them here and just solving is not the same as this formula. They don't work out the same. Okay, so this formula allows you to find the trig function values for angles that can be written as a sum of a special angle for which you know the trig function values. Okay, so we're solving for an angle we don't necessarily know the exact value for, but we can break it apart into special angles and then use those special angle numbers to solve. Okay, let's take a look at this example. For this example, it says find the exact value of the cosine of the quantity alpha plus beta if alpha equals pi over 4 and beta equals pi over 6. So putting the information right here into our formula, using our unit circle. All right here. So I am looking for the cosine of pi over 4. Remember, the cosine is the first term. So the cosine of pi over 4 is square root of 2 over 2. The cosine of pi over 6 is square root of 3 over 2. The sine of pi over 4 is the square root of 2 over 2. The sine of pi over 6 is 1/2. And then we multiply this out and we solve just like a normal math problem, right? Combine like terms and solve. Obviously, we can't combine these two radicals because they're not the same thing. They want an exact value, so there's not going to be any decimals, okay? And there you have it. That's how we use this formula right here to solve for exact values of terms that we know added together, okay? Let's look at another example up here. Find the exact value of the cosine of 105 degrees. So it says to express, since we don't have on our unit circle of 105, right? Express 105 as the sum of two special angles, 60 degrees and 45 degrees, and then use the sum formula. Again, the cosine of 60 degrees is 1/2. The cosine of 45 degrees is square root of 2 over 2. The sine of 60 degrees is square root of 3 over 2. And the sine of 45 degrees is the square root of 2 over 2. Add them together, combine them, reduce what we can, and there is where you end up. Okay? So, important to have our unit circle available to us. I had to run and go grab mine real quick, but it's important to have it available to us. Now, they're going to talk about even and odd identities. So it says, recall the following about functions. A function is even if f of negative x is equal to f of x, and an even function is symmetric with respect to the y-axis. A function is odd if f of negative x is equal to negative f of x, and an odd function is symmetric with respect to the origin. Remember, you can determine if a graph is symmetric with respect to the origin if you turn it upside down and it looks the same. Okay? Here is a breakdown based on the graphs of the trig functions and the use of reference angles. You have the following identities: even, odd, odd, right? Cosine of negative theta is equal to cosine of theta. Secant of negative theta is equal to secant of theta. Sine and those are even. The sine and the cosecant of negatives are negative, so they're odd, and the tangents are odd. So the only one that's even here is the cosine and the secant. The other two are odd. Let's turn the page. At page 18, we are going to read about the cosine of the difference of two angles. Now, they have a little bit about this formula as well, but the formula is here. So the cosine of the quantity alpha minus beta is the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. So don't get the two formulas mixed up. If we're adding, there's a subtraction sign in between. If we're subtracting, there's an addition sign in between. All right, so you only get one sign of each. When we're adding, we've already used up our plus, so this one becomes negative. When we're subtracting, here's our negative, there's our positive. You can think of it that way. You only get one of each. Here's our example. Given alpha and beta are first quadrant angles, sine of alpha is 3 over 5, and the cosine of beta is 12 over 37. Find the exact value of the cosine of alpha minus beta. Well, this isn't enough information because not only do we need the sine of alpha, but we also need the cosine. And not only do we need the cosine of beta, but we also need the sine. So they set up their reference angles, basically. And then we can use the Pythagorean theorem and solve for the missing part. And then we'll know the sines and cosines. Remember, you're just using the fractional, the ratio representation. It says here it's not necessary to find the actual angle measures in this problem, since the formula only requires the trig function values, and that also will help us stay exact, right? They want the exact answer. If the angles are not in quadrant 1, be sure that the trig function values have the proper sign. These were both in quadrant 1, so they're both positive, but we never know. You got to make sure you're reading the instructions very carefully. All right, and then there's one last little bit about proving identities, and it says the cosine addition formula can also be used to prove trig identities. So they want you to prove that the cosine of negative theta is equal to the cosine of theta as an identity, or is an identity. So they started with this cosine of negative theta, and they broke it into two parts, right? Because, and it still hasn't changed the value of theta, because for it to be a negative number, right, it has to be subtracted from 0, right? It's got to be less than 0. So they broke it into those two parts. And now they can use the difference formula to solve this. And so they have the cosine of 0 times the cosine of theta plus the sine of 0 times the sine of theta. The cosine of 0, okay, is 1. And the sine of 0 is 0. So that cancels out this term, because 0 times anything is 0. 1 times the cosine is just the cosine, and so we end up right there as an identity, okay? For this example, it says, prove that the cosine of the quantity 1/2 minus theta equals the cosine of theta as, or is an identity. All right, so again, they have it set up. They've put it into their difference formula, okay? The cosine of pi over 2 is here, and the cosine of pi over 2 is 0. The sine of pi over 2 is 1. And so 0 times anything is 0, so that term cancels, and we have sine equals sine, okay? All right, let's take a look at a couple of these problems together. This problem here, number 31, it says find the exact value of cosine of pi over 12. And then it says hint, express pi over 12 as a difference of two special angles. All right, let's grab our unit circle. Remember, this was from Unit 2. Oh, and I don't have the page number, but it's the very end of the book where it has the review. And then I've been using this special angle chart as well, mostly because it has the tangent numbers on it, which is from Unit 3, Section 5, okay? But this unit circle I photocopied from Unit 2, wherever the 6th review. I forgot to write the page on here. Here we go. Now, they want us to express pi over 12 as the difference of two special angles. To get a denominator of 12 with what I've got going on here, I'm pretty sure it's not going to be the pi over 2 and the pi over 6, because those values are just too widely different, and I'm trying to get basically 1 over 12. And so the only ones that have a difference of 1 are 3 and 4. So let's give that a try. So I'm going to have the cosine of pi over 3 minus pi over 4. And I put the pi over 3 first because it is larger. Pi over 3, 1/3 is larger than 1/4, just in general. So when we give them a common denominator of 12, it's going to be bumped up, you know, that much larger. And then so it's going to end up being 1 larger. And here, I'll show you how that works. So we'd have to multiply this by 4, right? So it would be 4 pi over 12. And then this we'd have to multiply by 3. So it would be 3 pi over 12. And therefore, we end up with pi over 12, okay? Pi over 12. All right, so the cosine of the quantity pi over 3 minus pi over 4. So we take the cosine of pi over 3 times the cosine of pi over 4, and we add, because remember, we can only use a 1 plus and 1 minus. We already used the minus, so this time we're adding the sine of pi over 3 times the sine of pi over 4. The cosine of pi over 3, okay, is 1/2. The cosine of pi over 4 is square root of 2 over 2, plus the sine of pi over 3, which is square root of 3 over 2, times the sine of pi over 4, which is the square root of 2 over 2. Okay. Here, because I'm running out of space, here we're going to end up with the square root of 2 over 4. And here we are ending up with the square root of 6 over 4. So it's going to be the square root of 2 plus the square root of 6 all over 4. Nothing is reducible. They've written it in a little bit of a different order, but that's okay. The answer is B. All right, let's turn the page and look at some more. Let's take a look at problem number 33. So for number 33, grab my unit circle here. We want the cosine of 180 plus theta, the quantity 180 plus theta, okay? So that is going to be the cosine of 180 degrees times the cosine of theta, minus, because I've already used my plus, right, the sine of 180 degrees times the cosine of theta. All right, so the cosine of 180 degrees is -1. -1 cosine of theta minus the sine of 180 degrees, which is 0, times the cosine of theta. Now, 0 times anything is 0, so that's gone. So our answer is negative cosine of theta. Answer C. All right. I'm going to go ahead and let you finish the rest of these on your own. When you're done with that, meet me back here for this next part, which is the sine addition formula. The next part of this section starts here on page 21. It's called the sine addition formula. And it's very similar, but not the same as the cosine addition formula. So if we slide down here again, here's how they derived it. But the sine addition formula is the sine of the quantity alpha plus beta equals the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. So in the cosine one, we were multiplying cosine times cosine. Here we're splitting it up, okay? So sine of alpha, cosine beta, cosine alpha, sine of beta. Okay, so let's look at this example. Find the exact value of the sine of 75 degrees. Well, 75 degrees is 30 degrees plus 45 degrees. And so that's what they have set up here. So it's going to be the sine of 45 times the cosine of 30 plus the cosine of 45 times the sine of 30. Using your unit circle, they've found the measurements that they needed. They added them together, and then here's their answer. All right, let's turn the page. As long as you have the unit circle, these problems are pretty straightforward. Here we are on page 22, and here is the difference formula, the sine difference. So we have the sine of the quantity alpha minus beta. And this time our sines actually match. So for the sine, our sines match. Okay, that's easy enough to remember, I hope. So we have the sine of alpha times the cosine beta minus the cosine alpha times the sine of beta. And they say, remember, you've got some things to remember here, but let's say here to find the exact value of the sine of pi over 12. Now remember, we figured out that that was pi over 3 minus pi over 4. We did that in the last problem. And so they have it set up here. They found their values, and then they added it or subtracted, in this case, it together, combine their like terms, and there is their answer. Now, you can also, just like with the cosine addition and subtraction, you can use the sine addition to prove trigonometric identities, okay? And so they want to prove that the sine of the quantity 2 pi over plus theta is equal to cosine theta. Well, they changed this here, right, and set it up. They found the values for their sine and cosine of pi over 2 and reduced. So let's look at this example. Angle M and angle N are in standard position. Angle M terminates in quadrant 2, and angle N terminates in quadrant 4. Okay, so personally, I'm just going to draw real quick. Here is my M, and here is my N, right? It says, find the sine of M plus N if the sine of M is 12 over 13 and the cosine of N is 15 over 17. They use the Pythagorean theorem, because remember here, so the sine of m is 12 over 13, okay? So that tells me that this is 12 and this is 13. Now, in this right triangle, okay, this is a special 5, 12, 13 triangle. Now, if you did the Pythagorean theorem, you would get 5, and that's fine. For n that terminates down here, the cosine, which is adjacent over hypotenuse, is 15 over 17. So this is the 15 and this is the 17. Solving that one, you would find this is 8. Okay, so again, it's a special triangle, 8, 15, 17 triangle. All right. Now I can use these ratios to solve the rest, which of course we are doing the sum. So it is the sine of m, which is opposite over hypotenuse, times the cosine of n, which is adjacent over hypotenuse. They gave us that one. Plus the, sorry, this is a -5, and this is a -8. Okay, plus the cosine of m, which is adjacent over hypotenuse, so that -5 over 13, times the sine of n, which is opposite over hypotenuse, which is 8 over 17. Okay, they multiplied these through, added them up, and they got 220 over 221. All right, so very similar. The next section here after we do a couple problems is the tangent addition and subtraction. That one's a bit different, so we'll take a look at that there, but let's take a look at a couple problems here. Number 40. The sine of 3 pi over 2 plus x. Okay, so we're adding, so it's going to be the sine of 3 pi over 2 times the cosine of x plus the cosine of 3 pi over 2 times the sine of x, right? We split up the terms. Now, the sine of 3 pi over 2 is here, right? Here's 3 pi over 2. The sine of 3 pi over 2 is -1. So I have -1 cosine x plus the cosine of 3 pi over 2, which is 0, times the sine of x. 0 times anything is 0, so this is negative cosine of x, which is letter D. Let's see here. Let's take a look at number 43. So for 43, we have the sine of pi over 4 minus b, the quantity pi over 4 minus b. Okay, so it's going to be the sine of pi over 4 times the cosine of b minus the cosine of pi over 4 times the sine of b. Okay, now the sine of pi over 4, here's my pi over 4. The sine is the square root of 2 over 2, so I have the square root of 2 over 2 cosine b minus the cosine of pi over 4, which is also the square root of 2 over 2, times the sine of b. Okay, now these terms have a common factor, and that is the square root of 2 over 2. And when we pull that out, we're left with cosine of b minus sine of b. So square root of 2 over 2, cosine b minus sine b, letter C. Okay, don't get too flustered when things don't actually cancel or zero out or whatever. Nothing we can't handle, okay? All right, let's do number 46. For 46, we have angle theta and not theta. I'm not sure what that means. I'd have to look it up, and I don't honestly care enough to do that. So we have two angles, and the angles are in standard position such that the sine of theta is -3/5, and theta terminates in quadrant 3. So I'm a visual person. I want to see it. This one is theta. Its sine, which is opposite over hypotenuse, is -3/5. Okay, and this, if you work with right triangles enough, is a 3, 4, 5 triangle. Now, Pythagorean theorem would have gotten you that 4 just fine. The tangent of not theta is negative 7 over 24, and it terminates in quadrant 2. Of course it does, because I've written in quadrant 2 already. So this is a 4. All right, here's my quadrant 2. Oh, goodness gracious. My tangent is opposite over adjacent. My adjacent is going to be, opposite, which is 7, over adjacent, which is the negative 24. Okay? Opposite over adjacent. Because remember, on our coordinate plane, right, this is negative x, these are positive y's. All right. 724. I can't remember if that's a special one or not, so let's just work it out. 7 squared plus negative 24, the quantity squared, equals c squared. I'm grabbing my fancy-dancy calculator, and we know that 7 squared is 49, plus 24 times 24, which is 576. Add the two numbers together, and I get 625, which I believe works out perfectly. Let's see, where, I always forget my square root thing. Here, answer, close your parentheses. All right, so c equals 25. Now, I have all the parts of all the triangles. I can now figure out what they want, because we haven't even looked yet at what they're asking for, right? We're just solving for our pieces. Now they want the sine of theta plus not theta, okay? So that is going to be the sine of theta. And actually, since we've already figured out our triangles, I'm just going to write them in. So the sine, oh, this is my not theta, which looks like this. The sine of theta is going to be negative 3 over 5 times the cosine of not theta, which is negative 24 over 25, okay, plus the cosine of theta, which is adjacent over hypotenuse, or 4/5, times the sine of not theta, which is opposite over hypotenuse, or 7/25. Okay, they don't give you a lot of space to work, so we're scrunching it in here. 5 times 25 is 125, okay? Negative 3 times negative 24 is 72, yeah. So I have positive 72 plus 4 times 7, which is 28. So I have 100 over 125. Obviously, 25 goes into each of those, and it's going to end up being 4/5, which is letter D. Oh, it isn't. Okay, go there. Letter D. Okay, I wanted to do that one with you because not that it's super complicated, but it's slightly more complicated. I find it, like here's the example here. They didn't actually go through finding the other term that they needed, but they do it in a fractional way. I prefer to not have to worry about the fractions, so I like to draw it out and do it that way. Whichever way you do it, as long as you're coming to the right answer, that's key, right? So pick the way that works best for you and just keep chugging along. All right, go ahead and finish these, and then we will look at the tangent sum and difference. Real quick correction here on problem number 46. This is supposed to be a negative right here. This is supposed to be a negative 4/5, which would make this a negative 28, okay? Which would then make this 44 125ths, okay? So not D, but B. All right? Watch your signs. All right, we're all human, right? But watch our signs. All right, page 24, we start talking about the tangent addition formula. Now, this one, they don't lay out, like the other two, it said, this is the formula, right? They don't do that for the tangent. I don't know. I don't know why. No rhyme or reason that I can tell. But the tangent of the quantity alpha plus beta is equal to the tangent of alpha plus the tangent of beta over 1 minus the tangent of alpha times the tangent of beta. So, like I said, this formula is a little bit different. Never in my life have I asked you guys to memorize any formulas, but please know where to find them. I don't think this section has a just like a wrap up of them, but here, like I told you, back in the back of the book is a great setup here, starting on page 44. Well, really, it starts on page 43 with the reciprocal and the quotient identities. Then we have the Pythagorean identities, the even odds, the addition formulas, all three. Right, here's cosine, sine, tangent addition, and then subtraction, cosine, sine, tangent, subtraction, and then we haven't got to those yet. But so page 43 and 44, super helpful when you're doing your homework, taking your tests and quizzes, okay? So that is the tangent plus. It says this formula can be used to find exact tangent value of an angle that can be expressed as a sum of two special angles or angles whose reference angle is a special angle. So find the exact value of the tangent of 195 is the tangent of 150 plus 45. Okay, and they have it set up here. And then using your special unit circle, but really more this chart, okay, is quite a bit more helpful, because we know that the tangent of 150 degrees, or 150 degrees, right, is here. But its reference angle is 30 degrees, right? That is the reference angle. So the tangent of 30 degrees, which is pi over 6, or 30 degrees, right, is the square root of 3 over 3. But because it's 150, this, oh, and I'm not even on screen, sorry, I'm so sorry. Because it's 150, tangent is negative here, and that's why they have a negative square root of 3 over 3, okay? And then the 45 degree angle, the tangent is 1. So it's negative square root of 3 over 3 plus 1 over 1 minus the negative square root of 3 times 1. Okay, so once you found the numerator, all you do is you multiply those two numbers in the denominator and subtract them from 1. And obviously, we've got a lot of fraction work going on to get down to the final answer of 2 minus the square root of 3. So unit circle and this little chart here in book, what was this? Unit 3, section 5, page 75 is valuable in doing this work, okay? All right. Taking a look over here at another example. Find the tangent of alpha plus beta, given that alpha and beta are first quadrant angles, and then they gave us the sine of each. Now, I like to draw it out, okay? That's just how I like to do it. They are doing it the fractional squaring way. They're not really showing you all the steps, but I'm not a big fan of squaring not that I can't, obviously, but I'm not a big fan of it. I feel like it just draws in more errors. So I would personally just draw out both of these triangles, and obviously one's a 3, 4, 5, and one's a 5, 12, 13. They're just the special angles. Find the tangent, put them in, and solve. This time it doesn't work out as clean as this. It's 56 over 33. I would just leave it that way. I wouldn't make it a mixed number personally, right? Up here, we have the difference of two tangents, or two angles, okay? So the tangent of the quantity alpha minus beta is equal to the tangent of alpha minus the tangent of beta over 1 plus the tangent of alpha times the tangent of beta, okay? So if we use our minus here, because our minus is there, then we have to use a plus in the denominator, all right? So that's the subtraction formula. Taking a look at this example, the exact value of the tangent of 15 degrees, well, it's going to be 45 minus 30. And so they set it up like that. The tangent of 45 is 1. The tangent of 30 is the square root of 3 over 3. But remember, there's that minus in between. Over 1 plus 1 times the square root of 3 over 3. Again, fraction work. From this stage, they multiplied both the numerator and the denominator by 3 to get rid of the two little denominators, and then simplified, right? We have to multiply by a conjugate here because we have to get rid of this radical. We cannot have radicals in the denominator, right? And remember, for those who maybe don't, the conjugate is the exact same denominator except with a different sign. So in this case, it would be 3 minus the square root of 3 over 3 minus the square root of 3, right? Don't forget to distribute properly, okay? Because it's this times this. And that gets rid of our radical in the denominator, and then we can get a simple answer. All right? Okay, let's turn the page. One last note here at the top of page 26. It says the tangent formulas can be used to prove identities, just like all the rest, okay? Just make sure you're following carefully along. All right, let's take a look at problem number 49. We have the tangent of 50 minus the tangent of 20 over 1 plus the tangent of 50 times the tangent of 20. Now, apparently they are going with decimal values here because we don't have those numbers perfectly worked out. Actually, now that I look at this more closely, they're asking you what is it that they asked to solve for. So they're kind of doing it backwards, right? This is the formula already set up because they're looking for the tangent of 30 degrees, okay? Because the tangent of 50 minus the tangent of 20 is the tangent of 30 degrees. So that's what they're looking for. That's what they're asking. We don't actually have to do any math for that problem, okay? We're going to look at a problem here on the page 27. The life test is in between. I just folded mine in half to get it out of the way. But we're going to come over here and look at problem number 54. If I wasn't struggling so much. All right. Angle A and angle B, alpha and beta, are angles in the standard position such that A terminates in quadrant 1 with the sine of 3 over 5. And B terminates in quadrant 1 with a cosine of 5 over 3. I'm going to draw them separately because they both terminate in the same quadrant. I don't want to have to deal with them being in their each other's way. So here's my A and here's my B. Okay. It's got a little stick. All right. The sine of A, which is opposite over hypotenuse, is 3 over 5. This is a 3, 4, 5 triangle. Okay. And I'm not a big memorizer, but sometimes you use things enough that you just memorize them out of, use. And so I don't feel like doing the Pythagorean theorem. If you didn't know it, use the Pythagorean theorem to solve for 4, right? This is our right triangle. Okay. Beta also terminates in quadrant 1, and its cosine is 5 over 13. Remember, cosine is adjacent over hypotenuse. Using the Pythagorean theorem, you could solve and see that this is a 5, 12, 13 triangle, okay? They're just a couple of special right triangles that exist. Now, they want us to find the tangent of alpha plus the tangent of beta, okay? Remember, that is going to be the tangent of, well, what is our, I guess, since we have our thing set up already, let's just do it. Well, I want to write it out. So this tangent of alpha plus the tangent, oh my gosh, tangent of beta over 1 minus the tangent of alpha times the tangent of beta, okay? That's what we're going for. So the tangent of alpha is opposite over adjacent, 3/4, plus the tangent of beta, which is opposite over adjacent, or 12/5, all over 1 minus 3/4 times 12/5. Okay? Now, I can reduce here. This can become a 1, and this can become a 3. So in my denominator, I have 1 minus 9/5. Okay? Here in the numerator, I have to have a common denominator, and that common denominator is going to be 20, right? Because 5 is the biggest number. 4 does not go into 5 evenly. So we multiply values of 5 until we get to one it does go in evenly to, and that is 20. 4 to get to 20 would be multiplying it by 5. So 3 times 5 is 15. Plus 5 needed to be multiplied by 4 to get to 20. 4 times 12 is 48. Okay, that's where we're at thus far. Continuing to combine things. 15 plus 48 is, let's see, it's going to be 363 over 20 over this one, because my denominator here is a 5, is the same as 5 over 5. So we have 5 over 5 minus 9 over 5, which gives me a negative 4 over 5. Now, I cannot divide a fraction by a fraction, but we are going to flip-flop multiply or multiply by the reciprocal. So I have 63 over 20. Remember, the numerator does not change, times the reciprocal or the flip-flop of the denominator, which is still negative, but now 5 over 4. Okay? I'm going to reduce. My 5 goes into 5 once. There's 4 5s in 20. I'm going to end up with a negative 63 over 4 times 4, which is 16. 63 is what? 9 times 7. And they don't have anything in common. So negative 63 16th this is. And so it's letter A. All right? Okay. I like to draw it out. If you just wanted to jump straight into the Pythagorean theorem, and go for it. I like to see what I'm working with personally. And however you like to do it, I would suggest at the very least starting with drawing it out. And if then in the future you don't need it, then don't continue to do it that way. But drawing it out always gives you something to reference as you're working on your formulas. Okay? All right. Finish these. That's it for section 1 of this book. As always, if you have any questions, don't hesitate to contact me, and I will be happy to answer them to the best of my ability. Otherwise, until next time.